Hello and welcome back to Precalculus1, section 2.1 on polynomial functions. So, polynomial functions are a little bit wide family of functions. You learned some already, so it's a bigger set, right, than what you have learned so far. What do you know so far? You know that you can have y equals a number, let's say c, whose graph is a horizontal line through c. So that's one example. Then you have y equal mx plus b. That's another function that is also in the same family, and that is obviously your linear line. This puppy, there is a b right there, was a y-intercept. So you know that function. Then we also know the function we learned last class, y equal ax squared plus bx plus c, or the other form, ax minus h squared plus k, but primarily the one on the left. And this one was your quadratic function, right? This is your x squared right here. And this is what we have for that one. So these are the three functions you already learned. Horizontal line, it's called a constant function. Any number you plug in, it always returns the same value, right? So if y equals to 3, at every x you plug in, you always get answer of 3, right? So that's why it's called constant function. Answer is constantly 3, right? Then you have y equal mx plus b, and the one that we beat to death last time, right, which is quadratic. Now, what are polynomials? Well, polynomial is a much wider family that includes higher integer exponents than 2. So you can encounter x cubed, and x to the 7th, and x to the 145. All of the exponents, integer exponents that you can think of, they can appear in what we call a polynomial as a family. So what is the definition of a polynomial? Polynomial function, we can call it p of x. You can also call it f of x, but we said p for polynomial. a0 plus a1x plus a2x squared plus a3x cubed plus ... plus an minus 1 to the xn minus 1 plus an x to the n. And that is what we call a polynomial. Now, I'm going to see. Right, we can do this one. So, do we all understand the index notation, which is a, and then you have a little number here, 0, a1, a2, as opposed to a squared or something? Do we all understand the small numbers here? They're counting numbers. It just says that a0 is a different constant than a1. So instead of me writing A, B, C, D, E, F, G, and so on, I can just put A0, A1, A2, A3. So it's just saying new next number, right? But not next number. Like, it's not that A1 is 5 and then A2 has to be 6. No. They can be any numbers inside the variable. It just says that this is your first variable, this is your second coefficient, constant, and so on. Not variable. Variables are x. So now, if I am to delete this much, If I am to kill all of this, gone. What do I have over here? Which one? Y equals C. I have this one. You see that? Because that's just, we know that this notation over, so this is just Y equals C. This is a constant function. Okay? What if I go and I kill this? What's left over there? Y equals mx plus b. Look. Y equals mx plus b. I know that your m is now a1 and your b is a0, but, right, we can name them whatever we want. Now, do we also see that I can make it for x squared? And then x cubed and so on. So, this one is the definition that can go as high as you have to go, like with n, right? Now, the term at the end is the one with the highest exponent. We call that one, right, the one at the end, we call that one leading term. That one has a leading coefficient and so on, because that's always going to be the one, right? So the highest term is always the leading term. So I have to write that. It's also very important. So term with the highest degree is the, so term with the highest degree is the term that you would name your polynomial after. So term with the highest degree is the leading term. And because it's a leading term, you are going to name the rest of the polynomial that way. So here is an example. If you have, let's say, f of x equals 3x squared minus 2x plus 9, the leading term is 3x squared. The highest exponent is 2, so we will call this quadratic, and we can also, we'll see how much impact all of this is going to have as we go down the line. So, these are all the things. Next order of business is to say that highest degree equals the order of the polynomial. This is a place where you get tripped on the exam too, for some reason. Please remember this one. Highest degree equals the order of the polynomial. So my highest degree in the upper one is 2, so the order of that polynomial is 2. So in this case, if I have g of x is equal to 9x to the 7 minus 6x to the 5 plus x minus 1, we would say degree equals 7. Or order equals 7. 7th order polynomial. Whatever wording is, right? But that's what it means when you say the degree, right? Which is directly connected to the exponent of x, the highest one. And this leading term is going to be the most important creature of this section and, in some sense, most of the chapter. So leading term is the boss. Let's see what we can learn from leading term. Just want to make sure that okay. So now, leading term. Test. This is a red subtitle, which means insanely important. I am going to call the leading term, as we had before, an x to the n. That's our leading term. We had it before. I hope I labeled it. Did I? Oh, I didn't label it. So let's label it here. Leading term. I know it's going to trigger you because you want the leader to be in front, right? Well, we live in sad times. We don't have that anymore. Leaders hide behind the regulations, right? And let you do the stuff. So what we have is an x to the n, and what we have is term which consists of two parts. Part number one is called leading coefficient. And part number two is just called variable part. Both of these will have a crucial role in our chapter 2. Now, I am going to start with exponent first, which is the n, and then we are going to go back and see what an does for us. Exponent n can be even or it can be odd. And that helps with the shape of the graph. We will have detailed examples and charts to see how this works. Right now, I'm just saying you can have a square, which is even. You can have cube, which is odd. You can have 7th power, that's odd. So just very simple, even or odd. And then you have the coefficient, leading coefficient, but coefficient an, which could be positive or negative. And this helps with orientation of the graph. You must know both to graph x to the 9, for instance. So now, how do these help you draw a graph? Well, before we get into the chart that will spell out rules, I am going to give a couple of examples from graphs you already know. So we can kind of establish some kind of connection. So the graph y equal mx plus b is a linear graph, and I'm just going to draw a line like this. What do we notice here? We notice that one side of the graph goes forever up, and the other side of the graph goes forever down. Do we see that? Mm-hmm. That's what these arrows are for, right? So left side goes down forever, right side goes up forever. But how about y equal x squared? What do we know? What do we see about this graph? Both sides go up forever. Thank you. Now, we should know, also, let's go here, x cubed graph, which is the squiggly line going through the origin. what do we notice about this graph?
One side goes up and one side goes down forever.
Perfect. One side up, one side down. Now, can we connect that to anything? And then tell me what the connection is? Let me see. Who's the detective over here? Well, our detective is not here, but...
Well, the domain range is the same as that X plus B.
Oh, you went so far ahead, my friend, but you're right. Domain and range for all of polynomial functions, for all of them, all infinity of them, will always be negative infinity to positive infinity. We'll get there. Can you connect x cubed to any other function, and why would you connect it to any other function?
Y equals mx plus b, because like the power is odd, like it's 1.
There you go. So visually, we get to connect mx plus b with x cubed because one part goes up, one part goes down, right? They both have that feature. And the link between them is they're both odd. Now I'm going to draw x to the 4th over here. It's going to look very similar to x squared. What it does, it kind of hangs. See, x squared goes immediately up at the point, and this one kind of hangs out around the minimum point and then goes up. So that's the difference between x squared and x to the 4th. But what do they share? They both share the same feature of they both go up. So what do we learn even in a battle, even versus odd? We learn that polynomials with the highest degree being even will have to have both sides of the function look the same way. And then you can flip it with a, and they can both look down. Now, that's the other part where the leading coefficient kicks in, right? So now we can finally draw a chart. And this chart is red chart, the theorem chart, right? The one the one thing you know. Okay, now, first of all, these are divisions. This is not XY graph. This is just me working on a chart over here. So make a chart with 4 boxes and make it as big as possible. There we go. That's not in the middle, so it's triggering me. There we go. That's better. So now, what goes into this chart? Well, on top of this chart, I'm going to say even and odd, and then I'm going to say a bigger than 0 and a less than 0. There's your setup. Even, odd, a larger than 0, a less than 0, and you will be using this chart to fit all of your polynomial functions from y equal mx plus b to 3x to the 107 minus, and so on. All right, let's go. For even functions, when the function is even and a bigger than 0, you will have 2 sides of the graph look up. Now, the graph over here is going to do something. I don't know what the graph is doing in between. That's not the part of what we are learning. Even looks the same way, and a coefficient being positive, it opens up. We learned that last class, or reviewed that last class. Go down in the below, right? It's going to have both of them look down. And whatever in between. So this is what I have for larger than 0, less than 0. Then we have odd. For odd, we know that one end has to look up, one end has to look down. So it's going to look like this, with something in between. And finally, if you flip that, it's going to look up, it's going to look down, and do this. Yes?
Even and odd, that's for the
Power, highest power. We call it the degree, we call it the order. So the highest power that you have in. So x squared, right? X squared is the biggest one, right?
Yeah.
So let's sketch a couple of these functions. We don't know everything about it, but we know enough to at least sketch a function. Sketch y equals x to the 6 minus x cubed plus 9, whatever. Well, this is the one we dissect, and we say a equals to 1, positive, and the exponent n is 6, which is even. And that's all I need to know. I don't need to know anything else to just sketch the function. We're not drawing the precise graph, right? Because if you want a precise graph, you have to have points. It has to go to particular points. Right now, this is just a sketch. I don't even have to put x and y axis. I'm just interested in the shape of this thing, right? But now, what do we know? If it's an even exponent, they both look the same way, and because a is positive, they look up. Yes, right? So you have to understand it's a two-step procedure. You are not memorizing that 6 is looking up, right? What you are memorizing is that it's a two-step procedure. Even means both sides of the polynomial function look the same way, right? And then a will determine whether they look up or they look down. Does that make any sense? Cool. So the graph for this, right, knowing these two pieces of information, means that the graph is going to look something like this. I don't know, whatever is in between, but it's going to look like that, right? Cool. So that's called leading term test. Okay, we can do that actually, and then that's gonna be okay. Now, the story that I'm going to start now is going to be expanded on in 2.5, but we have at least little preview of, right, the easy cases are here, and then the spicy ones will be, right. So sketch. Yeah, it's okay to sketch, but we can do a little bit better. If you are able to find all x-intercepts and y-intercepts, you can do considerably better on your graph, right? So what I am going to do now is I'm going to pick a problem from the book, because me making these problems up is not going to work out nicely. And we are going to use factoring to solve this. So now all of the problems in this section are factorable. The ones that are later are not, but we'll learn more, techniques to take care of that. So right now, I'm going to pick a problem, and we are going to look for stuff over here. Let's go. So to get better graph of p of x, which is a polynomial, we find x and y intercepts. X and y intercepts. That's what we have. And we have x and y intercepts. And then the x intercepts, I gotta write this in blood now. X intercepts are also called roots, are also called solutions. So x-intercepts have also these names. Find the roots, find the solutions, find x-intercepts. All of those words mean the same thing. It means where the graph cuts through x-axis, right? That's that. So we don't have to do whatever in here. We'll know exactly what happens. And I'm going to pick an example that it's factored, and then we'll deal with the rest, with factoring and things later. So let's start with some simple stuff. Let's say y equals x minus 2, x plus 4. I need you to tell me what is the order of this polynomial. 2. Perfect. Because the highest exponent when you FOIL this thing is going to be a square. So order equals 2. How about A? It's 1. Do we actually care that it's 1? We don't care it's 1. I heard it somewhere. Who said it? Positive. So we only care whether it's positive or negative, right? To get, is it 1? Yes, it is. You're not wrong, right? But we don't actually care what its value is. We care whether it's positive or negative. Now, obviously, you can get a positive or negative just by multiplying, right? Negative with positive, you get a negative. Positive, positive, you make positive, and so on. So now, we here see that a equals 1 larger than 0. And what do I know? I already know from this information, I already know that I'm getting this, right? That's what we just learned. Now we are going to add x-intercept to the mix. So we solve x minus 2, x plus 4 equal to 0. X minus 2 equal to 0, x is 2. X plus 4 equal to 0, x is negative 4. This is called zero product property, where you have the product of the two equal to 0, and then you set each one to 0, and so on. Now we can draw a much better graph. We're going to find negative 4 on x-axis. We're going to find positive 2 on x-axis. And now we know that it opens up, both ends look up. So we can just connect all of this mess. And this graph is much better than a random sketch we had before. But we have to be able to factor and find the exact x-intercepts that this thing goes through. We can also figure out that it goes through -8 on the y-axis, because you can find the y-intercept by setting all x's to 0. And if you set all x's to 0, you just have -2 times 4. And that's going to be -8. So we also know that the y-intercept here is -8. Now, this is obviously not a good drawing, so it looks terrible, right? Because look, my 4, right? You see that my length for 4 is bigger than the length for 8? You see that, right? Yeah. Let's take a look at more complicated case. F of x equals -2, x plus 1, x minus 2, x plus 6. What is the order? 3. What is A? That's it. That's all I need. A is negative. A is -2, but it's negative. Well, cool. What are the roots? Do we all agree on this? When you set each one of these parentheses equal to 0 on their own, they will give you -1, 2, and -6. So those are roots. Now, by what we learned earlier in that big chart, what do I get to draw as the, what we call, end behavior from here? What do I get to draw?
1 up, 1 down.
Perfect. 1 up, 1 down. And now, which one is up, which one is down?
Left side's up, and right side's down.
Left side's up, right side's down. Good. Now, that is something you memorize from the chart. That's, here's a chart. We had exponent 3. That's odd. So it's one of the 2 pictures on the right. Our A is negative, so that means it's this picture here. It's not a guesswork, right? That's why we needed the order. We needed the order so we can, as exponent, so we know which column we go into. And then we have our A, which is bigger than 0 or less than 0, to know which one to pick out of 2. So when you saw your exponent is 3, well, it's one of these 2. Once you saw that A is less than 0, it's that one. So that's how we know these 2. This is called end behavior, coming back in Precalc 2, coming back in calculus, obviously. So make sure you can do this. So now, what do I do? Well, to graph this one, I'm going to start by plugging in all of my x-intercepts. I have x-intercept at -1. 2, 3, 4, 5, and -6. And then 1 and 2 right there. Please watch how's this done, because it turns to be confusing. The lines have to be connected, and they have to go through these lines. But it's not the end of the story. They don't always go through the x-axis. We still haven't talked about it yet. There is something called multiplicity of the root. That's next, and then we're done for tonight. And then we'll deal with the rest of the lecture next class before the review. This example now, we start by, since this is my root that it's all the way to the left, I will start my arrow up there, and I will have the arrow down over there. Because those arrows should always be outside of the roots. Now, each one of these roots is a single root, which we call multiplicity 1. I'll come back to that in 2 minutes. Don't worry about it. If the root is a single root, you just shoot straight through the x-axis. Great. So, we shoot straight through the x-axis. We shoot straight through the x-axis. Do we see that we need to bend so we can go through the other point? So I need to bend over here so I can cut through this one and then bend to meet that one, right? There's only one way this can go. I mean, this is not something that, there's only one way this can go. I'm going to do this graph one more time from scratch, and then we'll talk about multiplicity, and we're done. Since each root is a single root, we call that multiplicity 1, M1 for all of them. They are multiplicity 1 because each one of these parentheses had the power of 1. So they all returned a single root on the bottom. So when we have M1 roots, they shoot straight through this. Then we need to still go through this root. Well, that says that this has to bend to meet that root and then bend again to connect to the line, and we have a function which was the one that we had. Now is the time to take a look at multiplicity, and then we are, yes?
How do you know at what point it bends and starts coming up?
You in calculus.
Okay.
In calculus, you will be calculating those points. Right now, we don't have the tools for those.
So we just kind of estimate?
It is, yes.
Okay.
So if you did this, full credit. If you did that, full credit.
Okay.
All right? We don't know now. Unless you go and you pick -3, compute in a function is going to spit out the y value, so you kind of know. But this is all about sketching. In Precalculus1, you are going to set the derivative of the function equal to 0. It's going to spit out those special x values, and you will compute the y's, and those will be the min and the max of a function. So there is a way to do that. Very simple, very easy, straightforward. It's a procedure you memorize and do. But it's not a part of this course because we don't know about the derivative yet, which is a calculus concept, right? So it will take you about 2 months in a calculus course to answer your question. From the first day, 2 months in, your question will be answered. So stay tuned. Work hard, and then you'll definitely get there, right? Here we go with the multiplicity talk, and we go home. Multiplicity of the root. Unfortunately, uses the lowercase m just like a slope. Please don't confuse them. Single binomials, like let's say x minus 2, will produce a root x equals 2, and we'll call that multiplicity 1. If you have x plus 3 squared, we'll produce root x equals -3, and that's going to be multiplicity 2. It makes no sense, but it will eventually. If you say x plus 1 cubed, it will return the root of x minus 1, and that's going to be called multiplicity 3. If you have x minus 6 to the 4th, that will return the root of x equals 6, and the root will have multiplicity 4. If you have x plus 2 to the 5th power, the root would be x equals negative 2, and multiplicity will be 5. What is the pattern that we are picking up?
Powers of multiplicity.
The power on each binomial is the multiplicity. The power of each. Now, why is that so? And what does it mean? Well, what is the meaning of x plus 3 squared? Meaning of x plus 3 squared is x plus 3 times x plus 3. So this one will return negative 3, and this one will return negative 3. Two of them, right? But we just say you can't graph negative 3 twice on one axis, right? Does this make any sense? So when I say I have a root x equals 5 with multiplicity 1, you understand that on the line there is number 5, and then there will be a root that just cuts through. If there is x equals 5, but it's a multiplicity 2, what happens is, right, can you graph two different 5s on the same line? Right, because that's what multiplicity is. Two separate roots, but each one is 5. So how does that manifest itself with graphs? It's a bounce, quadratic bounce off of the x-axis. And that's your M2. X equals 5, M3. What do you think is going to happen now? You still have only one 5. What do you think it happens with the root?
Won't it nu around the 5?
Yes! It is going to go woo! It's going to make a cubic squiggle through it. Like that. X equals 5, multiplicity 4 is going to do what? Same thing as 2, except it's going to be wider, right? Because it hangs longer, right, around this one. So instead of going, see how this one 5 goes straight up, right? Right away bounces off. This one is going to come in, hang around a little bit, and then bounce off. So multiplicity 1 is going to cut straight through. Straight line right through the root. Multiplicity 2 is going to bounce off as a quadratic. Multiplicity 3 is going to snake through like a x cubed. Multiplicity 4 is going to make the u, and the u is going to get wider and wider for multiplicity 6, multiplicity 8, multiplicity 10. You always have, right, by the time you are at multiplicity 48, it's going to look like this. Right? It's going to really, right, and this is where your 5 is going to be, right? So multiplicities now will help you bounce the function properly. So here is the last example for tonight. We are going to review this again and pick it up next class. Y equals negative 4, x plus 1, x plus 3, x minus 4 squared. Yes.
For earlier, if they had a multiplicity of 5, would it look like 3 just stretched out more?
Excellent. Yes. And you know what? That's actually worth adding to the list, because I did stretch the even one, and I did not stretch this one. So you win. X equals 5 with multiplicity 5 is going to look exactly like the cubic one, except it's going to be wider. Oh, this is just a root. So it's going to shoot through 5, it's going to come in, it's going to hang longer, and then, right, because the cubic one just did this. This one is going to come in, bend, hang around, bend, then bail. So it's wider. Excellent. Please, what is my order?
5.
4.
Wow, we're going to take it outside now? Is it 4 or 5?
4.
I just want to know how many x's I have on a pile. And we are going to say 1, 2, 3, 4, right? Because that's a squared one. We're just going to go 1, 2, 3, 4, right? 1, 2, 3, 4. I have 4 x's, order is 4. How about my a? Less than 0. What do I know about this?
Up and down.
Yeah.
Going up and down. Always. So, over down.
Okay, so please, both look the same way, and then they will open down, right? So, that's our end behavior. Order is even, they both look the same way, but it's negative a, so they're both gonna look down. Awesome. Help me with roots. What's the first root?
-1.
What else do I need to know about it?
Multiplicity 1.
Multiplicity 1, thank you. How about the next root? What's its multiplicity?
2.
-3, what's its multiplicity? 1. What's the exponent of the, right, it's 1. What's the next root? 4. 4, right? What's the multiplicity? 2. Time to draw the graph and go home. -1, -3, +4. Ready? I'm going to draw my end behavior that I got from the chart to the left and to the right of all roots, right? They have to be outside because the rest of the function is going to fit going inwards. So now, as I start on the left, please look at the board. Forget about writing. Forget about writing now. This is something that you learn by observing and mimicking later. I'm going to start here. I'm going into the root called -3. What is my multiplicity on the root -3? So what do I have to do when I go to -3? Shoot straight through. Boom. Now, I know I have to bend and go back to -1. What do I do when I hit -1? Go straight through it. So bend, go through -1. Do you see what needs to happen now in order to connect into the red and have a 4 to be your root? Do we see what needs to happen? We need to bend back and then bounce it off of the 4. Well, isn't this bounce a quadratic bounce for the even multiplicity? It will always fit. There are no exceptions to the rule in mathematics ever. If your graph is not fitting the puzzle pieces to match the multiplicity with the root, something is out of the order, right? You get to talk about exceptions to the rule in law, right? You get to talk about exceptions to the rule that there is no popcorns and deers, right? You only have deer. right? So exception to the rule. House, houses, right? There is an S at the end. It's a living nightmare for me to memorize all of the exceptions in the language, right? You were born with it, right? You grow into it. But many times I said popcorns, and I was corrected, obviously, right? So I learned. But that's exception to the rule. When you are dealing with this, there will never be a situation that there is an exception when the rule will not be followed. If it's not fitting, you are doing something wrong. You counted the order wrong. You looked at the A wrong. You have the wrong order for roots. You see that my -1 and then -3 in the middle, right? Well, -3 should be all the way to the left. So you have to be very careful, right, to arrange numbers, smaller to largest. But the bottom line is that the graph will always fit perfectly. And if any one thing is out of the ordinary and order, there is a mistake somewhere, because we do not have exceptions to the rule. All of them are always perfect. Yes?
Wait, so how do you know like which multiplicity it is, like for the roots?
Look at the powers on each of my parentheses. For -1, exponent is first order, first power, multiplicity 1. First power, multiplicity 1. Second power, multiplicity 2. Now, we will do 5 or 6 of these problems next class, and then we'll go into the review. Right? Awesome. Any other questions, quick questions about this? Right. Kill it.